Okay. Now here I have our ubiquitous rotating beam, and I've got a small magnet attached here. And another magnet, and I hope this is aimed correctly, that'll repel that magnet. Even though normally when I get this magnet close to the beam, it's going to attract it. But the effect of this magnet is greater than the effect of the attraction of this magnet to the metal. I wasn't sure about that until I put it on there. Okay, well now, come on back here. Okay. Now it's conceivable, well, it's actually not even conceivable, but you can imagine that I could follow this thing around with the magnet. Okay, keep following it around. I get it over here. Could follow it around here and accelerate it. Okay, by the repulsion of the two magnets. That's just one example of how I could, at least theoretically, maintain a constant force at the point of that magnet. Now, let's draw a picture of what I'm getting at. And of course, magnetic force is very tricky. They very well. You got something like an inverse fourth power force. So we'll talk about what that means later. Okay, now here's the beam rotating about its center. Here's the position of the small magnet. And I draw the big magnet close and keep the big magnet in the same proximity to the small magnet so that the force on this thing is always perpendicular to the beam as it rotates. Okay. Makes sense? Now, this don't have a meter stick, but okay. That magnet happens to be at a distance of approximately 10 centimeters from the axis of rotation. How much force do you think the magnet was producing when I brought it near and tried to follow it around? Okay, so the magnetic force is constant, it's about 0.8 newtons. Now, how much work does the magnetic field do per revolution? Okay, so how much work per revolution? We got a quick answer. There's an extra zero in it, but that's not a problem because I know what you were thinking. In a revolution, okay, well, you go 2 pi times the radius, 2 pi times 0.1 meter, which is about 0.6 meters. And you multiply that by 0.8 newtons, and you get something approximately, maybe it's 0.49 joules. Fair enough? That seem reasonable? Okay. Well, that's pretty good. How much work for radian? Okay, how much work for radian? That's 0.08 joules. Okay. If it's 10 centimeters, we're going to call R. This is F mag, F mag. In terms of the symbols, how much work do we get to move through angular displacement delta theta with a force F mag applied at distance R? Okay, so I'm going to say, I'm going to use the delta in front of W because I've got a delta in front of theta. It's F mag times R times delta theta. Okay. If F mag is unchanged, R is doubled, what happens to the work done? Okay, well, if R is double, doubles R delta theta, so just from the formula, you know it's going to double, right? Matter of fact, doubling R and leaving everything else the same is clearly going to double, just in terms of the formula. In terms of the physics, the formula isn't the physics. The formula comes from the physics. Okay. Just in terms of the physics, if you double R delta theta by definition of radian, which is the distance through which reasoning it out through the physics, so delta W doubles. Now, again, if you just have a formula and don't understand any physics, you can see it's going to double. But we're not here to use formulas without understanding the physics. Physics says delta W double. You know, I had to drag that out of you, but you had the right answer immediately. Okay. So we want to be sure that we know what the physics connections are. Because right now we're making a transition. We're transitioning to angular motion and angular dynamics. And this is where I think people really start to put physics together pretty nicely. Those who do. Yeah, I think everybody learns quite a bit from this process, even those who don't completely master it. All right. There's a name for F mag R. There's a name for this product. I don't want to give it that name yet. I'll do one more thing. Okay. Now, I used a magnetic force there because it's the easiest thing to demonstrate. Now, it wasn't demonstrated accurately, but it's the easiest idea to comprehend. Okay. I could have used a pulley, like we talked about last time, with a weight on it and a constant force. That would have worked also. But I wanted to do that because the pulley doesn't allow us to exert the force in a weird direction. So if I take this system and keep the magnet, where's this thing want to head? Okay. Maybe we can see it better this way. Except it wants to rotate. Settle down and we'll be able to do this. Okay. Now, if I keep the magnet here, and I can accelerate this thing with a constant force. That force was being exerted pretty much perpendicular to the incline or to the beam. Now, if I bring it in from this direction, well, that's going to get a little bit weird because the magnet wants to attract the metal beam more than it wants to repel the small magnets. It's not actually going to work, but you understand, I could exert a force in this direction. I could exert a force in this direction. Does that make sense? Okay, so that's one. I could put a rocket engine on it too. Or put one of those toy rocket engines in this thing. That'd be dangerous. You wouldn't want to do that. Thinking, then like crazy, and if it was unbalanced, probably kill somebody. These are cost sticking. Okay. So we got this constant force here. What happens at some angle phi. I don't want to use theta for this angle because we use theta as our kinematic variable position. Okay. Now how much work? How much work do we get out of this per revolution? Okay, so well, what we'll want to do to figure out how much work this thing does is work is the dot product of the contribution of the work is the dot product of the force with your direction of motion or with your displacement. Now your displacement's around a circle, so we just look at one point and say, okay, the force here splits into two components. It splits into a component here, which is F parallel, and a component here, which is F perpendicular. Parallel and perpendicular component of your force. And this component does no work. This component just pulls on the axis. Whatever's holding this thing, stationary at this point, right? This force does the work. So the revolution thing moves through a displacement or a distance of 2 pi r. And the force is always, we're following the thing around with the magnets, this force stays perpendicular. If you like, you could think you've got a little fan on this thing, and the fan's pointed this way. So as the fan spins, it exerts a force in the air, which exerts an equal and opposite force on the fan and causes it to rotate. Okay, got a little fan. They didn't have to hook up to some external motor. That'd be kind of a cool thing to do. Probably exists, you might just buy one of these days. Okay, so anyhow, there's your force, there's your displacement in the direction of force, right? Or the force in your direction of displacement. Okay. And I'm going to write that as that's, think before you write. That's going to be a clumsy expression. Let's see that. Put the 2 pi out in front. Okay. Much work in a delta theta rotation. Well, it's going to be just like before. We get a kind of like a W, delta W equals, I'll write it this way, x perpendicular times r delta theta. And I'm going to write this as follows. I'm going to write this as 2 pi r sine phi. And it's not 2 pi. It's supposed to, it's all, one of these going to be down. Okay. So did I do it better this time? Yes. That perpendicular times r delta theta, there's no 2 pi in it. So when I rearrange this and put the sine phi in there, I should have written 2 pi. Anyhow, there it is. Okay. Now that's equal to tau delta theta. Tau FR sine phi. Call that torque. And I use the delta in front of delta here in anticipation of the fact that we're sometimes going to have to integrate a force that isn't constant. And then you break it up into increments. And each increment gives you delta W sub I and all that stuff. Okay. In any case, there we have a non-calculus definition of torque and the work done by a torque. It's the work done by a constant torque. You'd have to integrate tau with respect to theta if tau was varying with theta. And it does in many cases, and we'll see one in a minute. Another picture. Same picture. Now I'm going to express F as a vector. And I'm going to express R as a vector. And I'm going to say torque, which is a vector, if I've got my cross product in the right direction, it's R cross F. What's the direction of R cross F? What do you mean by that? Oh, okay. Yeah, I'm seeing that, and I think it's probably a good answer. Okay, so I got an answer that was kind of like this. And what does that mean? It's in the Y direction. And then I saw people with their right hand, and same person, oh yeah, out of the board, R cross F. Okay. R cross F out of the board. Okay. Now the torque, then, the torque that accelerates this thing is not a vector in this plane. It's not a vector that follows this thing around here because that's not a constant vector. If I'm exerting a constant torque, then that torque can't be in the plane. Okay. If I do the right-hand rule, if I have an F here and an R here, I do R cross F, I find that the torque is perpendicular. So the torque is in this direction. And when you talk about precession and a few other things we'll talk about, maybe by the end of the week, you have to have that picture or you can't understand it. Okay, so the torque has to be that way, among other things, because it explains a whole lot of stuff. Okay, it explains what happens if you grab that spinning bicycle wheel and try to turn it this way, and it goes this way. Okay, have you ever done that? Have you ever seen that done? Anybody? Okay. Now we've actually, I think we got a bicycle. Don't want anybody to get hurt. We might still use it. Okay. So there's your whole idea of torque, and this gives rise to rotational dynamics. Definition of work. It's an integral over appropriate limits. Tau dot d theta. And when you think about these angles, the angle between tau and d theta is also, okay, if this thing's rotating, then right-hand rule tells you the direction of rotation. Okay. So if my torque is exerted by force here, the direction of the torque is here. Okay. If this thing is rotating in this direction, the direction of rotation is here. And the torque and the delta thetas or the d thetas are in the same directions, it's going to speed up. Now, if it's rotating in this direction, then your torque is into the board, whereas your omega, okay, is into the board. So your delta thetas are into the board. So your torque's going to slow the thing down, and the work is going to be negative. Okay, they're in opposite directions. So if you got a clockwise rotation with a counterclockwise torque, it's going to slow things down. You're going to get a negative integral, your work is going to decrease. your energy, total energy is going to increase. Makes sense? It's a framework. You want to get the framework before you work through the details. And the framework I'm giving you is kind of complementary, as in like the complement of an angle. I'm not paying it a compliment. Okay, I could, because I think we do a pretty good job. It's complementary to what you're seeing in the text. And the text, therefore, would be complementary in the sense of complementary angles. Okay, I'm not sure they would give me compliments. Okay, there we have it. Okay, well, let's consider another thing now. Let's consider the situation we have masses on this thing, okay? These masses are going to have kinetic energy, right? We talked about that last time. If this is a light beam, and it isn't, the beam has about 4 times the mass of one of these magnets. Okay, but if it was a light beam, then all the kinetic energy would be in the magnets. By light, I mean of negligible mass. So if the masses on the beam are much greater than the mass of the beam, and also far enough from the axis of rotation, then you have what we call a light beam. Okay, not a beam of light, but a light beam. Okay, strong light beam. Okay, so I'm doing that. And finally, I restrain myself from stopping this. It happened a while ago and I stopped it with this arm, luckily, because I got that tennis elbow in this arm. And if my reflexes take over, I'm going to rip it out. It's going to be another year before it heals. And it's irritating me. Okay, well, it's my own personal problem, not yours. Okay, let's see. Where was I before the disaster? Yep, okay. I'm going to put a mass m over 2 here and m over 2 here, where m is the sum of these two masses. And they're at equal distances. These are actually considered point masses, even though like the magnets aren't really point masses. We'll worry about the difference between what you get. Well, we'll do the parallel axis theorem later. Not going to worry about that right now. Okay, so here we have this. Now let's say that we have a torque exerted by some force at angle phi. Here's the light beam. Usually I'll say a beam of negligible mass. I want to take the time to write that up. Okay, so this is going to go from rest let's say from rest through 1 revolution, because it's fairly easy to calculate. Okay, from rest through 1 revolution, and the camera is all blurry. Hang on. The camera's not blurry. I can see the camera perfectly well. Be specific. Focus. makes the board look blurry. Okay, and there it is. Okay. Okay, so we'll go from rest through 1 revolution. What's the speed of the masses? Okay, how do you get the speed of the masses? Well, you do what you know how to do. What we know how to do at this point is calculate the work done by the net force. Okay, so do what we can. Then figure out the rest. It's FR sine phi times 2 pi. Okay, because 2 pi r is how far you go, and F sine phi is a component of the net force. And I'll change that to net force. Be explicit. Meaning that that's the only force acting on the system. Now, in reality, you're going to lose a little bit of energy to friction, a little bit to air drag. It's not going too fast. The air drag will be pretty negligible. And the beam itself does have some mass. Okay. But we're assuming that that mass is negligible, making a negligible contribution to the kinetic energy of the system. Most of the kinetic energy, practically all of it, is in the magnets. All right. So we find the work. Okay. And this is W net, change in kinetic energy, which of course is the change in 1/2 mv squared. Okay, the mass turns out to be just m. In this case, m in the equation stands for the general mass, but I also use little m here. Okay. So just to be explicit, I'm going to put a little pointy hat on these m's. So the mass m used in the theorem is m hat. And V naught is 0 because we're going from rest. Now it's m hat. 1/2 m hat Vs squared is 2 pi Fr sine phi And that's just a formula, but if you got numbers you put into it, it makes sense. Then it could be plus or minus. But actually the plus or minus in a rotation is just going to be plus for counterclockwise rotation, minus for clockwise rotation. So the point is, we calculate the work. That's easy. We just did that. We learned how to do that. So we invoke work energy theorem, since you have a test in that this week. You know, we want to see this as an instance. You also want to know how this is derived by plugging A equals F over M into the equation. V squared equals V naught squared plus 2AS, or 2A delta X. Okay. And then rearranging it to get net work, which is your F delta X equals this expression. Okay. That needs to be fresh in your head. Because if you're into reasoning out a problem and don't know where your formulas come from, it's easy to get stuck and pull out the wrong formula. Now that's ideal. Okay. In any given pretty good physics class at a pretty good university, only half the students can actually do that. But be in that half if you can. Because you're going to have less, you're going to be less likely to get stuck. Okay. Now we want to think about what the acceleration of this system is. So how are we going to get a handle on that? Okay, just starting to get a handle on acceleration. This isn't the simplest way to derive it, but let's just go ahead and do this because we've got all this information. Okay. In the preceding situation, delta theta is 1 revolution, which is 2 pi radians. And I'm using the V versus using omega. Omega F have everything there. Yeah. 4 pi takes care of it. Okay. If r sine theta is your tau net. So I'm going to use tau net, so I don't have to write all that out. Find the time, accelerate from omega naught to omega F, and then divide omega naught minus omega F by that time, and we have the acceleration, since it's uniform. Omega bar, we divide omega naught plus omega F by 2. We get pi times tau net. The time is 2 pi over omega bar, which is this way, 2 times the square root of pi over tau net. The algebra is pretty straightforward, so I'm just going to start it, but unless somebody corrects me, maybe somebody's about to do that. Okay, I was actually getting a little uncomfortable because I wasn't seeing any reference to mass in here, and I know we're going to end up with moment of inertia, which requires the mass and the radius. So I know that. And somebody asked me what happened to M hat over here. Well, when I did this step, I just did algebra and I didn't use any common sense, like I tell you not to do. Okay. Got to divide by M hat. I didn't even do the algebra right. Okay, which means now that over here, I'm a little happier actually, and grateful for the correction. We've got an M hat down there. It's probably hard to read. I didn't leave myself room to write it. And I'm going to have to rewrite this last expression. Anyhow, there's your time. So alpha, which I remind myself is constant, is equal to delta omega over delta t, which is 2 pi radians. And I'm not going to write out the intermediate step. If I'm dividing by this, then I'm just going to invert it again. Hopefully I've done everything right there. Okay, so it's delta omega over delta t, which is 2 pi radians times square root of pound that over m hat pi. That would be the square root of 4 pi pound that over m hat. And that's kind of interesting, but it's not particularly illuminating. Rather than try to pull that out of there, which I think I can do by substituting these expressions pound that, I'm just going to say, okay. Pound that is I alpha, where I is the sum of MR squared. Of course, my two masses are a distance r. I've got a notational error here. I've got to go back and fix that. So easy. I'm going to call this distance here r hat. This r hat. Because this distance really should be r. Okay. So now, if I'm talking about the torque, it is Fr sine theta. But now, since I used r for this distance, that was going to get really confused. So what we have here then is no problem up till where I just wrote this. I've got to use an R hat here. Well, this is actually getting more confusing than I expected it to, so let's just cut to the idea. And I is the sum of your MR squared. And I'm going to kind of leave that particular example. And I'm wasting a little bit of time on it when I get to this. But let's say so I got 4 masses here. For simplicity, each of these is m hat over 4. The angular velocity omega, what is the kinetic energy of this system? Assuming a strong beam of negligible mass. Okay. Velocity just actually it's usually written R omega, so let me put it in the usual order. And how do we know that? What's omega measure? It measures the number of radians per second, right? Okay. At distance r, how far do you move in 1 radian? You move distance r. So your radians per second, when you multiply it by r, gives you your number of meters per second. Okay. Does that make sense? Make sure it does, because that's fundamental to the whole radian picture. That's fundamental to this and a whole lot more. Okay. So V equals R omega. So now can we use that to figure out kinetic energy? Well, then we're going to be able to say this one has kinetic energy 1/2 times m hat over 4, because that's just what I found for the mass, right? Okay, so it's equal to all this stuff, right? Well, I'm going to claim that back out to omega squared. Okay. Then we're going to have a R2 squared plus R1 squared. We're going to have a couple of R2 squareds here and a couple of R1 squareds here. We've got a couple of 1/2s here. We're just going to end up with this. Okay. This equals the sum of our m hat r squareds I got a fraction in there that's irritating me. Hang on a minute. Is that 1/2? I think unfortunately 1/2 persists because the m hat over 4 is all add up to just an m hat. But each one still has a 1/2 in front of it. All right. This is still the sum of your mr squared. We get that 1/2, which we'd better have. And the sum of the mr squareds is I. Sum of your I omega squared. I mean, it's 1/2 I omega squared, where I takes account of the distances and masses of all these things in the entire distribution. Okay. We have this. We have this, which I kind of messed up the derivation. I'll take my word for it. These are vector quantities. Remember your right hand for rotation. You're going to keep seeing it. And this, which I think we did. The delta, the book doesn't. Especially a dot product. But for most of the problems you're going to be looking at, these two are going to be along the same line, maybe positive and negative. So your tau net delta theta might be negative, it might be positive. Very seldom will they make an acute angle with each other. Okay. That's the basis for dynamics. Doesn't this look a whole lot like 1/2 mv squared? Doesn't this look a whole lot like F net equals ma? So I like mass and alphas, it's obviously an acceleration. He's dealing with the alphas. Okay, it doesn't this look like a whole lot like force times displacement? Okay. Or it could be an integral of tau dot d theta. Okay. I wanted to say a little bit about, I get the moment of inertia length of the beam. Involves an integral. We'll probably talk about that later in this week.